Okay, good morning. Actually, it's afternoon now at my side. Good morning, everyone. So I'm would like to first thank the organizer to invite me to give a talk here, especially in the occasion of Gordon's birthday. So today I will talk about generic Hecke algebra and the theta correspondence over finite fields. And after the talk, I will say a little bit more about my interactions with Gordon. Okay, so this is so let's first talk about the math. And so this is a joint work with Zhou, Congling, and Jialiang, Zhou. And if so actually this this work the focus is not about the new result, of course, but anyway, there are some new results, but many parts of the knowledge of theta correspondence of over finite field is nowadays are already known due to the work of I think it should contain Jialiang and Srinivasan and Marie Aubert and Michel and Rouquier, and also a lot Shu-Yen Pan did a lot of works on this and give a lot of very detailed information of the theta correspondence over finite. By the way, also include should include Roger Howe and Sharma Gerbrich. They also did a lot of things for theta correspondence over finite fields. So we will focus basically on the part of theta correspondence which related to generic Hecke algebras of a Weil group, basically type BC Weil group. Okay, so this is a setting. So we will let F be a finite field with Q elements. And so this is the size of the field, and the characteristic is equal to P. So we will also fix a subfield of F, which is we call F is F naught, which will be either F or the quadratic subfield of F. Okay, so and then we will consider a vector space which is epsilon Hermitian vector space over F. It means that it has an epsilon Hermitian form, and the epsilon is in plus minus 1, and this is the common setting for theta correspondence. And we will let U V to denote the isometry group of the finite dimensional epsilon Hermitian space. So then we will consider basically the dual pair such that which basically determined by a pair of epsilon Hermitian spaces such that so we epsilon times epsilon prime is -1. So we will just simply add prime to all the notations, so to denote the things with respect to V prime. Okay, this is a table which would be familiar to most of you, I guess. So if we call we are in the type A case is if, of course, this F is a quadratic extension of F naught. And so then this UV and the UV prime will be unitary groups. And the other cases, F is equal to F naught. In this case, we need P is not equal to 2. Basically, it's due because Jialiang has worked out all the explicit formulas and properties for Weil representation for all these cases. Okay, later I will talk about this. And so for the unitary group, we do not assume P is do not need to assume P is not equal to 2. This is also the same situation also holds for Srinivasan's paper on the character formula of our uniform projection of the Weil representation, and also Maria Aubert and Michel and Rouquier's paper. So in the type A case, actually, you no need to assume P is not equal to 2. And I'm not very sure about Shu-Yen's work, whether he need this condition. Okay, anyway, I would like to say I will explain our approach to the question. So from the explanation, you will see that the residual heuristic, the heuristic is not that important in the approach, as far as you have a reasonably defined, well-defined about representation, a Weil representation. Okay, so the other cases are type B case. Basically, in this case, V is all-dimensional vector space with a quadratic form, and I should put symplectic group for the UV prime. However, for certain reason, I would like to pretend it's a metaplatic group. Okay, so in the type D case, there will be even orthogonal group, which is paired with the symplectic group. And so you can switch the role of V and V prime, then you will have type C case, which is symplectic group paired with even orthogonal group. And then you have the type C tilde case, which is the metaplatic group, but we call it metaplatic group, but actually it's a symplectic group over the finite field, because over the finite field you don't have a non-trivial extension, central extension of the symplectic group. Okay, so right, we are talking about theta lifting, but if you look at the definition of theta lifting over the finite field, then it's quite confusing at first sight. So basically, we will adapt the following definition of theta lifting. So, first of all, we need to fix the Weil representation. So suppose we have V and V prime, which are epsilon Hermitian space and epsilon prime Hermitian space. We can form a tensor product space, which will be naturally epsilon -1 epsilon Hermitian space. Then we will have a natural isometric group homomorphism from the product to this group. Okay, so then you can form a Weil representation following Gerardin, and so here for certain reason we need to fix the quadratic character of f cross when p is not equal to 2 for the case B, C, D, and the C tilde. Okay. And then we will, for each pair of Hermitian and epsilon Hermitian and epsilon prime Hermitian space, we will just define the Weil representation of the product group to be either the restriction of the Weil representation of this group, or a twist of the restriction by the quadratic character, where with respect to you will have the factor which is dimension or half dimension of V prime. So notice that here either V or V prime is always a symplectic space. So these two spaces are always symplectic space. So therefore, half makes sense. So why we need this modification is because in all the cases, we want the orthogonal group X geometrically in a Schrödinger model. Okay, so let's define the theta lifting, which rather actually it's a big theta lifting, which is the functor from the set of representation of V, UV, to the set of representation of UV prime, which is the multiplicity space, because we are in the finite group case. So we allow to do these things. So which is a multiplicity space of sigma inside the modified Weil representation. So this will have a natural UV prime action. So it's a contravariant functor. Okay, so this image is usually, in general, not irreducible in the finite field case, and it has no reasonable way. I should say there's no reasonable way, no good way to choose irreducible piece of it. I think Anne-Marie's first talk in this conference explains how to choose a canonical one among the big theta lifting. And okay, so this is about the definition, and we are focusing on understanding this small map and at least part of this map. So basically, we will try to understand the things interact with parabolic induction, and we will just look at the part of parabolic induction which related to theta. So this is our setting for the relevant parabolic inductions. So suppose we have epsilon Hermitian space, and we will use VL to denote the Hermitian space at L copies of the hyperbolic space. And we will fix a parabolic subgroup of the UVL such that its levy has a form that it's just L products of GL1. And we will consider the character of GL1, which is either the quadratic character of F cross. This is a quadratic character, so which is A maps to A to the power for Q minus 1 divided by 2, I think. Right. This is a quadratic character of F cross. Or the trivial character. Okay, so we will consider the induction, a parabolic induction from this character to the whole group. We call it JL sigma. So suppose you fix a sigma, which is a representation of UV, then basically we put sigma here and put the chi's at these places. Okay, so then we do the induction. So we call it a JL sigma. Okay, so we will introduce a notion. Let me call it as. Actually, I have no good way to define the notion, but so I just randomly pick it. So it's I call it theta cuspidal. The reason is that its behavior is very similar to the cuspidal representation under theta correspondence. So which means that basically is that its cuspidal support does not contain this character chi. Okay, so mathematically it says that this sigma does not occur in the induction functor for certain for any r which is bigger than 0, and for any sigma naught which is irreducible representation of smaller. So this is an irreducible representation of let's say UV not or maybe I should write VR, where VR satisfies the condition. Okay, so I use V naught. So this is a irreducible representation or representation of UV naught such that V is and V naught is in the same width tower, and the dimension of V naught is the dimension of V minus 2R basically. Okay, so this is the definition of theta cuspidal. So if you, so there's a lot of interesting properties for sigma, which it has if you compare to the cuspidal representation on the theta correspondence. So in particular, so all the cuspidal representations are theta cuspidal by this definition. So important feature is that you look at the first occurrence. So let's fix a width tower of epsilon prime Hermitian space. So this is epsilon prime Hermitian. And then we consider the first occurrence index, which is the minimal dimension of V prime in the width tower such that the theta lift of sigma is non-zero. Okay, so this is the first occurrence index, which is nowadays plays a big role in the theta correspondence, study of theta correspondence. Okay, so then we assume sigma is theta cuspidal. Then basically using CUDA filtration and arguments in Moglin, Vineris, Wasford-Jay's book. There's a chapter, I think chapter 5, something like this. It talk about the induction and the theta correspondence. Then you will see that the big theta lift of sigma, if sigma is theta cuspidal, is always irreducible and theta cuspidal with respect to, of course, with respect to the V prime as the first occurrence. Okay, and this is irreducible and non-theta cuspidal after the first occurrence. This is exactly as you just delete the theta. It exactly same as the claim for the cuspidal representation if you look at the MBW's book. Okay, so now let's assume the sigma is theta cuspidal. Okay, so we can have a very clean conservation relation. So the result is that if you look at the first occurrence index of the sigma, okay, so then the first occurrence index of the width tower with respect to this width tower V prime plus the first occurrence index with respect to another width tower. So which we call this V prime tilde be the companion width tower of V tilde. Okay, right, of the curly V prime, companion width tower of V prime. Then you will have the equality for the sum of these two first occurrence index, which equal to 2 times of dimension of V plus a discrepancy, which we call it delta. Okay, so the delta will be equal to 1 in this case, and the companion width tower will be the width tower of so for the unitary group, width tower will be the width tower of Hermitian space whose dimension parity of the dimension of the space inside V prime is different the parity of dimension of V prime. Okay, so this is parity of the dimension of space in V prime tilde is different from the parity of dimension of the space in V prime. Okay, so this is the type A case. And in the case of type C tilde, which means that UV is either symplectic group or the pretended so metaplatic group. Anyway, they are symplectic groups. Then this delta will be equal to 2, and you choose the companion width tower, which are width towers of quadratic space, so such that the parity of the two width towers are the same, but the discriminant of the spaces inside the discriminant of the spaces inside the tower are different. And for the type BD case, so the discrepancy is 0, And in this case, for the symplectic group, we know there's only one Wittower. So we just use the same Wittower. However, we define the occurrence. Sorry. So okay, we define the occurrence to be the actually what I should write is the occurrence of V prime sigma tensor determinant. However, I prefer to instead of twisted representation, actually, if you follow the have ever read the proof of Bingson and Chen-Bo-Zhu's proof on the conservation relations, they twisted this Weil representation instead of twisted representation sigma by determinant. Okay, so we will have this kind of first conservation relation. I would like to say this conservation relation for sigma is cuspidal, has been proved by Pan Shu-Yen using a reduction to the p-adic case. And also, for the general case, I think Pan Shu-Yen also proved it in the 2019 paper. Okay, but now we would like to prove this using give yet another proof of this the conservation relation. We use Hecke algebra. Okay, so let's consider. Basically, we will look at how this parabolic induction occurs. Since occurs related to the theta Weil representation. So the natural thing is that we consider the endomorphism algebra of the parabolic induction. Okay, so but this will obviously act on the multiplicity space of the parabolic induction to the Weil representation, and but the natural action is on the right. So actually, we prefer the left action. So we will use, instead of using this endomorphism of JL sigma, we will use the endomorphism of, so this is actually endomorphism of UBL of JL sigma check, which is a contragradient. And so it's not difficult to find that under the assumption that sigma is theta cuspidal, then the endomorphism algebra will have a natural basis. Okay, so which is given by this way. Let's assume W to be the normalizer of the Levy subgroup, and it is naturally isomorphic to the type BC Weil group, which is a symmetric group of order L letters and a semi-direct product with plus minus 1 to the power L. Okay, so then we will always fix the root system and fix the Tits lifting of the Weil group to the normalizer of the parabolic the Levy subgroup, and we will use W0 to denote the lifting. And then we will have a basis which satisfies simple conditions. One is that the support is the double coset of W0. And in our case, we can take that the value of at the W0 of this TW is equal to the identity map. Okay, so then by a theorem of Howlett-Leher, so we will know that this H is isomorphic to a Hecke algebra of WL. But wait, so there's a problem that this isomorphism, first, what is the meaning of Hecke algebra of WL? So in this case, you probably will have unequal parameter. And then, moreover, there probably will have two cocycle twisted of the Hecke algebra. If you look at their book and their paper on the I think called the cuspidal induced representation. Okay, anyway, so there will be a 2 cocycle, and for the unipotent representation, actually Lucic showed that the 2 cocycle is trivial, and in general case, Geck give a proof for the trivialness of this 2 cocycle. But anyway, this 2 cocycle thing is not obvious, and it's due to you don't have a net. Usually, you won't be able to extend sigma L to the whole normalizer. Okay, so we would like to solve this 2 problems. Oh, okay, so first thing is that the 2 cocycle things. If you read Howlett-Letter's paper, you will find that there's a lemma tell you that if H, the Hecke algebra, has 1-dimensional representation, then it will have it can imply that the 2 cocycle is trivial. Okay, the second is that okay, so we actually have a 1-dimensional representation, which coming from the theta correspondence. So recall that if sigma is so we always assume that sigma is theta cuspidal. Then we say that the big theta sigma is 1-dimensional, right? And you turn the table around, then you will see that sigma prime, if it's a first occurrence, then this one will be so if sigma prime is first occurrence lift of sigma, then this home space is 1-dimensional. Okay, so it's equivalent to saying that big theta is so big theta is irreducible. Okay, so then it's automatically, at least in our case, will tell us the 2 cocycle is trivial. And then what about the parameter? The parameter is about the quadratic relation. Basically, suppose you have a simple reflection in the Weil group, then you are expecting that you have this quadratic relation for certain C1 and the C2, which are complex number. Oh, sorry. Yeah, it should be non-zero complex number. So how to determine these 2 numbers? Okay, one method is if you have 2 different 1-dimensional representation, actually it's for the algebra generated by TS. But of course, we also, if we have 2 different 1-dimensional representation of the Hecke algebra itself, we can more or less determine these 2 numbers. Okay, so so in our case, we actually have another 1-dimensional representation, which is by change width tower. So recall that in the conservation relation, what we have 2 different width tower, and so we will do this computation to see how we normalize the parameter. So recall the thinking diagram of the Hecke algebra WL. So it's look like this, and we have S1 to SL minus 1, which contribute to the, so basically this part are the SL part, and the last one is the correspond to this 1, 1, 1, 1, and the -1, this one inside SL semi-direct product with plus minus 1 L. Okay. So anyway, so we have this thinking diagram, and it's quite easy to see that. Okay, so so the Hecke algebra we are talking about will be the Hecke algebra with defined over C and satisfy the condition that it has a basis. We call it curly T W, which for any W in WL, such that it satisfies that the usual braid condition relation and the quadratic relation with parameter Q for the simple reflections in SL, and additional quadratic relation which for the last root. Okay, so and the similar by the similar construction, you can construct the generic Hecke algebra, which is the is a free module defined over, say, attached to an indeterminate nu. Basically, you use the same formula but replace Q by nu. Okay, so the fundamental theorem is telling you that you can have some kind of globalization of a Q representation to this generic Hecke algebra, and then you will have kind of equivalence of category in a reasonable sense. Okay, so let's look at this Hecke algebra action in our case. So now our setting is that we assume sigma and sigma prime are theta cuspidal, and they are correspondent on the cuspidal. We are interested in considering this home space, which a priori it's U VL and J, I think JL sigma, but I think just from the Frobenius reciprocity, you will see that these two spaces are the same. So we will have unnormalized element basis of the Hecke algebra action on this space. So you can work out the action. It's pretty simple. That it's basically the action of any element W, which is a lift of the Tis lift of W, and the action of the unipotent part. But you don't need to the whole unipotent part. You only need the things which moves the unipotent part, which is non-positive after the W action. Okay, so this is the Dinkin diagram, and it's easy to see that it's the unnormalized operator already satisfies the braid condition, and for the things which inside the this symmetric group, it's already satisfied nice quadratic relation. However, for the last root, we don't have the nice relation, but we still have a quadratic relation, but with some constants. The first constant is a C, and another constant is A, and the value of A is easy to verify, to get. Basically, you just evaluate the convolution as an identity, you will get the value of A. So you can see that the value of A is equal to basically this one. Okay, so the chi is the either trivial representation of F cross or the quadratic character if in the C tilde case, and then times the size of the root group. So here comes this discrepancy sigma. Okay, this is the discrepancy sigma. And then C, so basically you have the quadratic relation that T minus D1. You want to find the quadratic relation like this, right? And so what you do is basically multiply them out. You will see that C is equal to C1 plus C2 and A is C1 times C2. Okay, so how to determine C1 and C2? So basically you use mixed models, and let's choose a Fourier transform, and then this related to Fourier transform. Let's fix the mixed model like this. So if VL is decomposed in this way, and it can be seen that the multiplicity space in our case is V0, which is one dimensional. It satisfies the condition the support is precisely at the 0. And the action of the last root is nothing but a partial Fourier transform. And then you can see that the partial, so we can compute the unnormalized action on this a vector, which is a partial Fourier transform, and the unipotent part basically is a truncation. Basically, if you have a thing which sit in the origin, the Fourier transform of a point will give you a line, right? And then you will truncate, and you will get back the line, get the point, truncate the things which is non-zero vector. This is precisely the situation, but because the Fourier transform is uniform, is a unitary operator, so you will have some. So this number is coming from the truncation, and this number is coming from the Fourier transform. It's a unitary operator, so it will map the unitary, so 1 to the whole space, but with the scalar. So the scalar is nothing but the dimension of V prime, half dimension of the V prime to the occurs in the Q power. Okay, and then you also have some Weil index. Okay, so a similar thing happens if you consider another weight tower. Then we will have that C1, which is the action of the operator TTL for the first occurrence multiplicity space for our original tower, and we also will have C2, which has this exactly the same formula, but with different dimension of space, and the important thing is that the Weil index is never equal to each other. So you actually can figure out the Weil index for the two different. First, the Weil index will be a constant on each weight tower, and the discrepancy of the two towers will be always -1. So therefore, you know the C1 and the C2 are never equal. So this will be the two eigenvalues of the quadratic relation of TTL. Okay, so therefore we know that C1 times C2 is equal to A. So what is A? A is easy to calculate, which is this number. Okay, so and the Weil index is the roots of unity. So if you take the absolute value of both sides and compare the power of Q, what you get is the conservation relation. Okay, so this gives a simple proof of conservation relation. And so it also tells us how to normalize the Hecke algebra. So we always do the normalization so that the action of the normalized operator on our preferred, so the case, the theta correspondence case is act by -1. So this is, therefore we have, so you can figure out that we have an explanation of the difference of two first occurrence index in terms of the parameter for the Hecke algebra. So the parameter of the Hecke algebra is basically half of the difference of the first occurrence index for two towers. And under this normalization, actually, we know that under Tist deformation, this multiplicity space is corresponding to epsilon L. This is the quadratic character of the WL, which is trivial on SL. Okay, great. So I think this is sort of the appetizer of the whole story. So we are actually interested in not the so this case is that we consider sigma and the sigma prime, and sigma prime is always theta cuspidal. Now we will consider the so-called High-Schneider series related to sigma and sigma prime. So we will think about this multiplicity space, which will tell you the theta correspondence for the High-Schneider series with respect to so this sigma and the sigma prime are always correspond under theta, and they are theta cuspidal. Okay, so then it's a result by observation by AMR, that theta correspondence only relevant to the representation occurs in induction of sigma L and sigma L prime. Okay. So the goal is to understand the Hecke algebra module structure of this multiplicity space. If you know the structure, then you will be able to figure out the theta correspondence. Okay, so of course we will just let H be the generic Hecke algebra, which is free algebra defined over this kind of ring. And we will have an operation called a specialization at any integer, at any number of Q, where we will embed R into CQ by mapping U into Q. Okay, so you will have a specialization. So our main result is that you will actually have H times H prime, where H prime is the notion for this generic Hecke algebra with respect to. So this is corresponding to U L prime L V prime L prime. Okay, so you will have a module which is called M, which is the generic Hecke algebra module free over the defining ring, such that its specialization at Q is equal to our multiplicity space, and its specialization at 1 is isomorphic to this kind of induced module. Okay, so from this formula, okay, so basically you have WL, you have WL prime, then we have diagonal WK inside here, and you have the rest of WL minus K and WL prime minus K. Okay, which we always put the quadratic character at this place. Okay, so with this result, plus Eden and Moyes result on the cuspidal unipotent cuspidal correspondence of unipotent cuspidal representations between on the theta correspondence, you will be able to recover Aubert-Michel-Rouquier's result and Pan-Shu-Yen's result. And if for this symplectic odd orthogonal group case, if you use Liu and Wang's result, you will also recover since has been worked out by Shu-Yen Pan. And okay, so I would like to have a comment is that Lustig and AMR actually use the normalizations that sigma, this parameter is always positive integer. In our case, this parameter can be negative integer. So our treatment is similar to, in some sense, similar to Pan's treatment. And if you want to change the normalization, it's mainly just by replacing certain epsilon by the trivial representation in the formula. Okay, so this also, so the main theory actually leads to a stronger form of the conservation relation, which tells you in general, if we take any representation sigma, we can define an integer which is basically a maximal L, such that this sigma occur in JL sigma prime for certain smaller sigma. Okay, I think I should say sigma naught in some sense. Okay, so anyways, this is a constant only depends on sigma. It's basically saying that in the cuspidal support of sigma, how many chi occurs. So it's this is a C sigma. So in particular, C sigma is equal to 0 is equivalent to say that sigma is theta cuspidal. Then we will have a general conservation relation, which saying that the first occurrence index for the two tower at the constant of this representation is equal to this number. And the delta is a discrepancy. Okay, I would like to say this relation is more or less obtained by Pan-Shu-Yen by a reduction to unipotent cases. Right, so there's, I don't have too much time, so I will just give some hint of what you do. So basically, we will use CUDA filtration, and then you will be able to compute the using the mixed model, and you will filtrate the space, the multiplicity space. You will view the multiplicity space M as certain subspace of the function space. And then you will see that the support of the function will be described in this kind of algebraic way, this geometric way. And then we will filter it in terms of rank of the map. And then, so we will actually have a smaller Borel subgroup and GLVL plus act on it. So CUDA's filtration basically tell you that you will have a very explicit vector space isomorphism between the orbit space to the multiplicity space. And then this M is actually already a smaller Hecke algebra. Actually, these tools are parabolic sub-algebras of the original big algebras. And it actually tells you that you have a generic Hecke algebra modules already for a smaller Hecke algebra. But anyway, so if you specialize at V equal to 1, then it's already tell you that the multiplicity space, a quite large portion of the multiplicity space, I would like to say. So the difference between SL and WL is you need to add one more generator. So the idea is to compute the action on the generator. So basically, the space has a generator which is, let's call it IK. So we be able to compute the action. So basically, the action is look like this. So we will compute the TTL action on IK, which is this kind of expression. It's very complicated, but it will have some term like this, and you also compute these actions. But anyway, so what we do is we will use statistic formation to set Q equal to 1. The amazing thing is that if you set Q equal to 1, these terms will vanish. Okay, so one thing is that all coefficient is in this ring, but I will not talk too much about this. But the important thing is if you specialize at V nu equal to 1, you will see that you will have a filtration, which is basically the filtration under the rank, and the quotient will be exactly this induced representation. So this gives us the proof of the theorem. So there's of course a lot of technical detail, and I would like to say that it's in some sense we only need to know the term has coefficient inside the brackets has coefficient in say Q to the power of plus minus half. But actually, my collaborators is be able to work out very precise formula for these terms, the coefficient of these terms. So which can also confirm this is true. Okay, so I think for the expert, you already see this will lead to the result of AMR and Pan Shu-Yen's result for the theta correspondence between these High-Chandler series. Right, this is 3 of the authors of the work in preparation. It always took longer time to write a paper. So hopefully we can release the paper in a very near future. And so I put this picture is because this is actually the first occasion when I had a serious mathematical discussion with Gordon. Previously, I think before 2012, I think I have met Gordon for several times at other occasions. But I think this as a IMS NUS conference is my first time which has a serious mathematical discussion with Gordon, and I think I was about to submit my thesis, and we are having some discussion of what is the correct definition of theta or big theta in some sense. And after that I have learned a lot of things from Gordon, and I think at the next time when we met is in Utah, and then we had a discussion of my thesis, and he was talking about the epipelagic representation lived under the exceptional groups. And so I'm talking about classical groups, but it turns out we have quite good interaction. And finally, and three of us is be able to write down a paper on the exception theta correspondence between epipelagic representations. And so after that paper, I think I didn't get too much chance to learn from Gordon. Hopefully next after the pandemic, we can have more collaborations. And happy birthday, Gordon.